In class, I said that for any two vectors, u and v, this quantity is always defined. I said this was true if those vectors are in the plane, so that, u is what we call a two vector, right? It has two entries. I said it was true if they're vectors in space, right? So three-dimensional vectors with three entries. On your final, you did this with four vectors, right? The vectors had four entries. My claim was, we didn't prove this in class, but my claim was that this is always defined, no matter how big your vectors are, right? Now, first off, let's just think about this. What would have to be true for this value to always be defined? If you think about arccos, the only values that you could ever put into arccos have to be, here's a hint, have to be between two values, and yes, they have to be between -1 and 1. And we can include -1 and 1. Otherwise, this just doesn't make any sense. You can't plug in arccosine of 2, right? And so, for this to be well defined, which I claim that it is, then this value must always be between -1 and 1. And so, when we are going to prove the Cauchy-Schwarz inequality. Proving that inequality will give us this. This itself is not the inequality. At least not quite. We'll see in just a second what it is. But I'll just go ahead and write this up here. The Cauchy-Schwarz inequality. For any two vectors, u and v, the Cauchy-Schwarz inequality says that the inner product of these two vectors, u and v, now let's just stop right here. I'm trying to be as general as possible because the Cauchy-Schwarz inequality works for any type of vector and any type of inner product. And so I'm using this notation here saying you take the inner product of two vectors u and v. And yes, you may have guessed that a specific type of inner product is indeed the dot product. So to say that otherwise, the dot product is a type of, it's a special type of inner product. And so, if you take the inner product of two vectors, you end up with a scalar. This is true for any type of inner product. That's one of the things about an inner product, is that you go from your vector, which in many cases has lots of entries, not always, but sometimes there are finitely many entries, like the kinds that we've been working with. Sometimes there's infinitely many, sometimes there's only one. In any case, with any type of vector, you take the inner product of it and you end up with a scalar. Okay, so that's what this represents right here. You've taken your inner product, two vectors, and what you have now is a scalar. If you take this scalar and square it, it will be less than or equal to the inner product of the vector u with itself times the inner product of v with itself. And again, right, these are just scalar numbers. So you have some scalar and you're squaring it. We're saying that's less than another scalar times another scalar. Okay, that's what this means here. Okay? Now, in the case which we're going to be working with, we're going to assume that our vectors, u and v, are real valued vectors in n-dimensional space. Okay, so in other words, what I'm saying here is that both vectors u and v are inside r to the n. What does that mean? Well, we're saying that, like we did in class, right, u is some vector. It looks like this, u1, u2, all the way up to un. And v is similar. V is a vector v1, v2, all the way up to vn. And all of those u's and v's are real valued. Now, it's also true if these are complex valued. So instead of u and v being in r to the n, if they were in c to the n, that is, each one of these guys was some kind of a plus ib. They had complex values. This is still true. And we could actually prove the complex case. It's not that difficult, but it is a little bit more intricate. There's certain things. The dot product is a little bit different with complex values, just a little bit. It's doable. I have faith in you guys. I believe that you could do it. You could handle it. It's a little out in the weeds, and I don't think that you'll get anything more by doing the full complex version. And since we're not doing the general version with any given inner product, or with a general inner product, let's just use the real value. So that's what we're going to assume from here on out, is that the vectors u and v are real valued, and the number of entries we have are arbitrary. That's why I chose n. I'm not saying R3, right? It could be any finite value. And yes, like I said before, there are vectors with infinitely many values. And what's cool is that this is still true if your vector has infinitely many values. But we can't prove that yet. So we're going to do this case here, the special case where both of our vectors are in r to the n. And the most common type of inner product, when you're in this space here, when your vectors look like this, the most common inner product is the dot product. So let's rewrite this in terms of the dot product. So the inner product of u and v would be just u dot v. We take u dot v. That's a scalar value. We take that scalar value and square it, and it will be less than what we would get if we took the inner product u dot itself, u dot u, and multiplied that by the inner product v with itself, v dot v. Again, these are scalars, just like I said. That's some value, you square it, it will be less than that value, whatever it is, times that value right there. Okay, now before we get into this, we are going to prove this, okay? And so this right here is called the Cauchy-Schwarz Inequality. These are two last names, Cauchy and Schwartz. Cauchy-Schwarz. This is the Cauchy-Schwarz inequality in its full generality. If you have any inner product and any vectors, this is always true. This is the Cauchy-Schwarz, I'm just going to abbreviate, Cauchy-Schwarz for real valued vectors. For real valued vectors with a finite number of entries. And this n could be arbitrarily large. It could be 10 to the 10 to the 10 to the 10, and you do that 10 to the 10 times and whatever, this is still going to be true, okay? All right. So before we move on into this, what I want to do is kind of pick apart what each of these little pieces are exactly. The notation that we're going to use will be useful in our proof, and it'll help us rewrite this in an interesting way. So first off, let's do u dot v. So u dot v itself is, you should have already anticipated, you should be able to just do this in your head. What is this? Yes, it's u1 v1, u1 times v1 plus u2 times v2 plus all the way up to the last entry, un times vn. That's what that is. Now it'll be useful if we could write this in a more compact way. We have a sum of something. Can you think of how we could do this? Yes, indeed. You're right. We use summation notation. This is the same thing as the sum as, now we need to choose some dummy index, right? Why don't we call it k? As k goes from what to what? How about 1 to n, right? As k starts at 1, then it goes to 2, then it goes all the way up to n. Of what? Well, it's the u, k's, v, k's. Check that, make sure I did that right. Is that? I think so. Okay. Now it's also going to be useful if we do the other one. So let's do u dot u. U dot itself. U dot u is, well, u1 plus u2 plus u2, or u2 times u2 all the way up to un times un, which you'll notice we could write that a little bit differently. This is the same thing as u1 squared plus u2 squared plus u3 squared, all the way up to un quantity squared. And we could rewrite this in a more succinct way, a way that will be helpful in our proof, as the sum of, you better be able to do this, do it before I say it, the sum, as k goes from 1 to n, of the u sub k's squared. Note, this will be very important in our proof, this is not the same thing as the sum, as k goes from 1 to n, of the uk's quantity squared. These are not the same thing. Let's see why that's the case, right? If you have, let's say, a 1 plus 2, and you square that, that's the same thing as 3 squared. That's the same thing as 9. But this is not equal to 1 squared plus 2 squared, because that's just 5. Last time I checked, 9 and 5 are not the same number, and so we just have to be careful. We will really want to be careful of this when we go to do our proof, because something like, say, not exactly this, but something like this will show up, and we need to make sure that we're not saying, oh yeah, the squareds, and so this thing is just squared. No, it's not. Okay, we're going to have to be really careful with that. All right, so that's all I'm going to say about that until we actually get to it. Then I'll remind you, okay? So similarly with u dot u, v dot v is the same way. V dot itself is the v1 v1 all the way up to the vn times vn, which is just v1 squared, all the way up to vn squared, which, yes, is just the sum as k goes from 1 up to n of the vk's squared. Each one of those are squared. Yeah. Okay. Now, recall this. Remember, what is this? I think we called this in class, we may have called it I don't think we called it the absolute value of u. I think we called it the magnitude of u. When you're dealing with inner products, we call it the norm of u. And in this case, when you're in R to the n, right, when your vectors are these types of beasts, then the length, the magnitude, the norm, they all mean the same thing. So as we do this, I might use those terms interchangeably. I might say, here's the length of u. I might call it the norm of u. Whatever. Now, what is this? If u is that bad boy right there, then the norm of u is square root of the u1 squared plus the u2 squared all the way up to the un's squared. Does this look very similar to something that's on the board? Yeah, and I'm pretty sure we either did this on a quiz. I may have had you prove this on a quiz, or maybe it was extra credit for a quiz or something like that. Or maybe you had to use this fact. I think you might have had it for homework. But if we have this right here, if we square both sides, well, we just take the norm of u and square it. What do we get? Well, we get this basically makes the It makes the square root go away, right? One thing to note, another thing to notice, this value, the norm of any vector in r to the n, is always a positive quantity. Why is that? Well, you have a bunch of squared real numbers. These real numbers squared, and you add them together, it's always positive, no matter what, right? There's never a chance that when you take real numbers and square them and add them together that you get a negative number. It's always going to be positive. So when you take a square root, and we're taking the positive square root, then this thing is always positive. So when you square it, nothing new is happening here. It's just whatever number this is, it's the square root of this number right here. We don't have to worry about the plus or minus in this case because we know that the magnitude or the norm of a real valued vector is always a positive quantity. Okay? So one more here. This right there is that, right? All the u's, the uk's, all squared, and you add them together. It's the same thing as u dot u. So this is just u dot u, right there. So the u dot u is the same thing as the norm squared. Similarly, the norm of v, take whatever that value is, and then you square that value. That's the same thing you would get if you took v dot itself. And so, we can rewrite this guy using these right here. That's what I'm going to do. I'm going to say, okay, you take u dot v, and then you square it. That is less than or equal to. This is now that right there. So I can say that's the same thing as the norm of u quantity squared times the norm of v squared. Okay, so again, this is just some scalar value and we square it, so there's just some number right there. That's just some scalar value, we square it, so that's just a number right there. That's just some scalar value and we square it, that's just a number right there. And so we're just talking about real numbers here. Okay. I want you, if you don't have this stuff, actually really this stuff right here written down somewhere, go ahead and write it down because I'm about to erase it and we are going to use this stuff over and over and over in our proofs. It might be useful to have this stuff written down, but I'm going to go ahead and erase it right now. We don't need this stuff anymore. Okay. Now, like I said, this value, forget about the squared right now. The norm of u is always, 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 no matter what, always a positive number. Okay? It might be 0, but I guess then your vector u is just 0. So let's not use any 0 vectors here because remember, if one of your vectors, the norm of one of your vectors is 0, you're dividing by 0, so none of this makes sense anyway. So we're only going to be talking about non-zero vectors, okay? And that's most of them, by the way. There's only one way to have a 0 vector, and that's the 0 vector. So we're not going to include the 0 vector in our conversation. So this is always positive. It's always strictly positive. It's always strictly bigger than 0 in our conversation. This value right there, the norm of v, is also always positive no matter what. But this value, before we square it, it might be negative. It might be negative. Yeah. In fact, it might be 0, right? I mean, you could have two non-zero vectors that when you dot them, they give you the 0 vector, and you take the inner product. That means that they're orthogonal. You should remember this. Okay, but here's my point here. And let's just actually, let's do, so you see what I'm saying. How about 1, 2, and v is, I don't know, 1, negative 1. When you dot these together, u dot v is going to be 1 times 1 is 1, 2 times negative 1 is minus 2, and so that gives you a negative number. In this case, u dot v is a negative number. And yes, when you square it, like, which is what you're going to do, you're going to take the inner product, take the dot product, you get a number, and then you square it, yes, it will give you a positive number. Why am I going on about this? Well, what really bugs me about this inequality is all the squareds there. You have, this is squared, this is squared, this is squared. Everybody's squared. It might be easier to write if, you know, we maybe get rid of those squareds. And if you're looking at the top of the board, the whole reason that we're talking about this in the first place, you'll notice that that's kind of where we're trying to head with all of this, right? And so let's take the square root. Here's the thing, since these values are always positive, when we take the square root over here, we don't need to worry about whether or not they're positive or negative. We know that it's always going to be positive, right? So we don't need to worry about this side. We could just take a square root and the squareds go away and everybody's happy. On the left-hand side, though, we're going to need to be careful. And we absolutely need to be careful whenever we're dealing with inequalities. So let's just take a break here for a second. We're going to kind of go over here. In fact, I'm going to use a different color. And let's say that we have some number that's squared and it's less than another, say, positive number. Because we know there's always positive. So let's take a number and square it. So let's take 2 and we're going to square it. And I claim that that's less than or equal to 5. Is that true? Yes, obviously. Now, okay, so knowing that this is positive, we could just take a square root of both sides and say, okay, well, since that's always positive, then it must be the case that 2 is less than or equal to root 5. And yeah, of course that's true. Okay. But what if the number we had started with was a negative number? What if instead of 2, what if I took negative 2 and I squared it? I claim that that is less than or equal to 5. And that's true. Take negative 2 and square it and blah, 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 you're fine. Now we take a square root. And does that mean then, does this say that negative 2 is less than or equal to root 5? Well, I mean, that is true, but this doesn't really help us much. Because, I mean, I guess it could if that's what you're trying to show. But my point is, like, if you know that this number is positive, then of course a negative number is less than it. It doesn't really matter. Like, in fact, I could say negative 100 billion bajillion is less than or equal to root 5. And that's true because it's negative. Who cares, right? But then if I try to go in the other way, I say, well, okay, well then let's square both sides. So negative 100 billion bajillion squared is less than or equal to 5. Well, that's not true. That's not even close to being true, right? What I'm getting at is with inequalities, we got to be really careful of how we're doing this. Okay, we don't want to just say, well, take square root of both sides and nah, you're good. Because, like, yeah, in this case that might be true, but we want something a bit more than that, okay? My point is this, you should kind of remember this, is like, okay, something happens here when we take a square root. Or rather, no, I don't want to do it that way. This is what I'm going to say. This is how I want to do this. My claim, here's my claim, is that if you take some number and then you square it, and then you take an absolute value. My claim is that this is the same thing as the absolute value of that original number. Now let's remember what absolute value is. It's just whatever's inside of there if x is positive or 0. It's the negative of whatever that is if x is less than 0. So this is my claim. So this is the definition of absolute value. It's just make it positive if it's not, right? If the number is negative, make it a positive number by making the negative there, right? If it's positive, it just stays positive and it's fine. And my claim is that this is the exact same function as that. That should be somewhat obvious, but let's use an actual value to make sure, okay? So on one hand, if x is a positive number to begin with, we take it and we square it, and then we take a square root. Well, 2 squared is 4, and the positive square root of 4 is just 2. And so yeah, is that the same thing as the absolute value of 2? Yep, okay, yeah, absolute value of 2 is 2, and so this also works out. Now let's do it with a negative number. Yep, negative 2. We're going to take it and square it, and then take a square root. And what this tells me is if this is indeed equal to the absolute value, this should be the same thing as the absolute value of negative 2. Right? That's my claim right here. And you can kind of see that that's true. Negative, absolute value of a negative is just whatever that number is, but positive. Or if you make the negative negative, right? It's negative, so make it negative, and it comes out to be positive. And indeed, yes, you take negative root 2 and you square it, you get 4. Take the positive square root of 4, and you do indeed get 2. And so I hope you believe this here, like that this is the same thing as that. We did not go into this we didn't spend much time with this in Algebra 2, but this is very useful. It's something good to know. And so, what do we have here? We have a number, and we squared it. Okay, a number, and you squared it. Now we're going to take a square root of it. And so, if I do that, that's what I'm going to do here. I'm going to take the square root of that. I'm going to take the square root of that, take the square root of both sides. Now, like I said, this thing, and actually let's break up my square root, right? The square root of a product is the same thing as the product of the square roots. Everybody should remember that. And now, since those never had the chance of being negative in the first place, they're just whatever that is. This is the same thing as just the norm of u, or the magnitude of u, times the norm of v. Okay, we don't have to worry. It was never negative to begin with, so this is just true. We don't need to worry about it. But this thing may have been negative. And so when we square it and then take a square root, what we end up with is the absolute value of this thing, u dot v, right there. Okay. I hope you followed that. Took about 1,000 words to say something that you probably should remember from earlier. But anyway, I just want to make sure that we're all good on that. So what I'm saying is this. Is that the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v, or the norm. Okay? So in other words, if this is true, if we could prove that this is true for any vectors u and v, then this must be true. But if this is true, how do we deal with the absolute value in an inequality? Let's think about this, and this is kind of what I was saying earlier. If the absolute value of negative 2 is less than the square root of 5, which is true, then the way, if you remember how we do this, it's that this thing, the magnitude of this thing, is bounded by this. Right, so if we're on a number line here, 2 lives here, negative 2 lives there, right? But since the absolute value of it is less than, we'll call this right here square root of 5, then the negative of it must be greater than negative root 5. right? And so the way we deal with absolute values of something, and here we'll just say any x in absolute value, if it's bounded, if its magnitude, if its absolute value, if its size is bounded by that, well, that means it can't stretch too far that way either. And so when you drop the absolute value bars, you get the positive up here and the negative down there. At this point, this going from here to here should just be rote. You shouldn't even have to think about it. You should be able to just do that. You see that and think, oh, that means that this is bounded like that. Okay? And so, for our, here we go, we have some number in absolute value, and it's less than some positive number there, because norm of u is positive, norm of v is positive, so the product is positive, and so what that gives us is that when we drop the absolute value bars, we get u dot v. It's less than the positive ones, but it's also greater than the negative of these things, negative u. V. Does that make sense? So if that's like 5, and it's bigger than something in absolute value, then that means that 5 is bigger than it, but negative 5 is smaller than it or equal to it, etc. Okay? Now look at this. How do we get from here to here? Well, since we said that u and v are not zero vectors, then neither the norm of u nor the norm of v is 0. So we could divide by the norm of u times the norm of v. And when we do that, right, I'm going to divide everybody here through by u, v. Here's my u. Here's my v. Here's my u. Here's my v. And we don't need to worry about absolute value signs switching. The inequalities flipping or anything like that, because, like we said, the norm is always positive. Okay, so this just stays the way it is. That divided by that, well, that's itself. And so this just works out to -1. This is something divided by itself, so that works out to +1. Lo and behold, that's what we want. If we could show that this is true, then this always works in there, which is the whole point of everything that I'm trying to do. Okay, and so let's just think about this. What do we need for this? Well, given any two vectors in R to the n, this is what everything hangs on. Because if we could show that this is true, and we've just shown that this is true, which means that this is true, which means that this is true, and we did that absolute value trick where we did the positive and the negative, and so therefore this is true. So this follows from this. All we need to do is, given this setup, if we could prove that this is true for any two vectors u and v, and not 0, I'm not going to say that anymore. We're going to assume they're non-zero vectors. If we could show that this statement right here is true for these two beasts, then it will be the case that this is true, which proves my claim that this is always defined, no matter what. Before we get into our proof, there are a few things that we need to make sure we're 100% clear on, because they're going to come up in our proof. One of those is that there's this axiom of real numbers, and I put axiom in scare quotes because depending on how you decide to construct the real numbers, you could either take this statement as an axiom, just say, well, it's always true. Whenever this is true, then this is true. Or if you've built up the real numbers from, and I believe it's a certain type of set theory called Zermelo-Fraenkel set theory, if you're interested. Then you can use other more basic axioms to derive this, and then it wouldn't technically be an axiom, it would be a theorem. But we're getting in the weeds here. This is just like definitional stuff that we don't need to worry. We're just going to call this an axiom. Now, this is always true, that if A is less than B and C is less than D, then A plus C is less than b plus d. And this also works if they're equal, right? Less than or equal to. That's cool. Now, one way you could see this is you take these two things and add them together. So in other words, what this axiom tells us is that you could add two inequalities together, and the thing you end up with, so I go a plus c over here, a plus c, drop the inequality down, and then go b plus d over here, b plus d. So what this says is that, in effect, if you have two inequalities, you can add them, and the thing you end up with is true. Does this work in reverse? That's the question. It's like, wait a second. Okay, well, if you could add two inequalities and you end up with something that's true, certainly you could subtract two inequalities and what you end up with is true, right? Well, let's see. So what I mean is, so here's this statement. We're saying, if this, then this. We can't exactly just go backwards from this side. We need a little bit more than that. But this is what I want to test out and see if this is true. I want to see if it's the case that a plus c is less than or equal to b plus d, and either one of these is true. Let's say that we know that a is less than or equal to b. Then, can we recover the other bit? Is it true that c is less than d? Is this true? Pause it. See if you could figure this one out. It turns out no, it is not. This is not true. And here's a counterexample. Okay, so first off, 3 is less than or equal to 100. You believe that? Yeah. Okay. So let me rewrite this. How about 1 plus 2 is less than or equal to, how about, oops. How about 1 plus 99? Yeah? Okay, so this is still true, yeah? Now, okay. So if this, yes, we got it. Now let's get an a less than b. Well, I claimed that 2 is less than 99. Yeah? And so then, if this is true, then the other part must be less than that. Oops, I'm sorry. I wanted to do 1. 1 is less than 9. It's still true. I guarantee it. 1 is less than or equal to 99. Well then, if this is true, then 2 is less than 1. Oh no, it doesn't work. So what I'm getting at here, now this kind of looks weird the way I did this, and I obviously fumbled this because I don't know, it's hard. But what I said earlier is that this means you could add two inequalities. You could add those two inequalities and the thing that you get remains true. And so what this is about is, can you subtract two inequalities? Can you subtract that from that and that from that? In some cases you can, right? Like in the case where 1 is less than 2 and 3 is less than 4, then yes, you could do this and you'd end up with something that's true. But in this, you can't do it in general, because look at this, right? Can I subtract these inequalities from each other? Well, I subtract there, and I get that 2 is less than or equal to 1. Oh no, it doesn't work in that direction. It works in one direction, but it doesn't work in reverse. We're going to have to keep that in mind. And why am I getting into this? Well, we're about to do a proof, aren't we? Well, let me just finish this. We're going to state it this way. This axiom, stated differently, is that u, y, you can add inequalities. But you can't subtract them. So we could add two inequalities together and get something that's true. But if you subtract two inequalities from each other, you're not necessarily going to get something that's true. You can't guarantee that you'll get something true. The same way that we just did, right? Now, why does this matter? Because we're about to do a proof, right? We're going to move in a certain direction. The thing I'm about to write on the board is that you should have this in your head whenever you're thinking about this. Probably like the fourth or fifth time I'm going to write this down, right? So let's say we want to prove that cosine theta is equal to 1 minus sine squared theta. Let's say we want to prove that that's true. And so we go, well, let's start with it, and now we're just going to operate. So I square both sides. I get that cosine squared is equal to, you square root, and you just get this. And you say, well, am I going to add the sine over to the other side? So you have cosine squared theta plus sine squared theta equals 1. And so you go, oh, that's true. Therefore, the original thing is true. Is it? Let's plug in a pi and see if it's true. Cosine pi equal 1 minus sine squared pi. Oops, pi. Cosine pi is -1. Sine of pi is 0, I believe. Let's just double check. Yeah, it goes through here, pi. That's sine, it goes through a pi, it's 0. So that's 0. 0 squared is 0. So -1 is equal to the positive square root of 1. -1 is equal to 1. That's not true. What went wrong? Well, it works in this direction, but going in the opposite direction doesn't work. Because if we actually did go in the opposite direction, we would have started here. We would have brought the sine over. So we go cosine squared theta equals 1 minus sine squared theta. And then we take a square root. And we get cosine theta is equal to, but when we take a square root, there's two possibilities. This thing is either plus or minus. And so we missed out on that. If we had started here with a plus or minus, then yes, this statement would be true, and you'd have to figure out whether it was plus or minus when you get to the end of it. But that's not what this says, right? This says we're claiming this is true. We end up with something true, and we go, oh yes, it must be true. We have to be very careful about this, especially with the proof that we're about to do, okay? We're going to be moving in one direction. We're going to start with the thing that we're trying to prove, and we want to do a bunch of operations to see if the thing that we get, we want to end up with something that is true. And we're going to have to stop and say, well, wait a second, do these steps reverse? Okay? And I'll be talking us through that the whole way. And remember the thing about this. You could add inequalities, but you can't subtract inequalities. But one way works, the other way doesn't. We're going to need to be mindful of that. Especially since we're going to start with something we're trying to prove, moving in a direction, hoping to get at something that is obviously true, and then we're going to say, okay, when we work our way back, are we doing this the right way? So this is what we want to prove. The theorem, and this is the Cauchy-Schwarz inequality for vectors in R to the n. So let u and v be vectors in R to the n. Then the dot product of those two vectors squared is less than or equal to the dot product of u with itself times the dot product of v with itself. And remember, we just showed that if we could show that this is true, then it follows that we get the thing inside that the quantity that we care about is between -1 and 1. Okay? So this is what we want to prove. Can you take a guess what type of proof we're going to do? I mean, come on. Right? We do induction. And you're going to hate me because I know I made this big stink about if you have the n in the statement, don't use the n. We're going to do induction on n. And we did this before, right? Where, yeah, it should be pretty obvious, like, how to do this. Why are we not doing induction on k? Because I like to use k for the subscripts. I could use I in the subscripts and everything. It's just I don't like to. I'd rather use k as a subscript, okay? Sorry. But this is exactly what we did for the binomial theorem. So we're gonna do the same thing here. I mean, by exactly, I mean that we used n instead of k, and then k showed up in the subscripts of our sums, etc., etc. And so we're going to do induction. Why are we doing induction? Well, think about it. Like, we need to show that this is true for any value of n. That should tip you off, right? Like, that sounds like an induction-like proof. Another thing you could test to see, is induction a good way of doing this? Well, think about what the base step would be. In the base case, n is equal to 1. Did that come as a surprise? Did you think that vectors had to have at least 2? No, vectors can be 1. And if you think about, what would this look like in the case of my vectors just having one entry? Turns out it's going to be really simple to prove. And so if you have something where the base case is really simple to prove, and you're trying to show that it's true for all n, induction is usually usually the way you want to go. Sometimes it's not, but in this case, indeed, induction is the way we want to go. So, let's do a base step. Okay. So in the base step, we're going to say, suppose. Oh, actually, hold on. I'm sorry. No, I didn't. I'm jumping ahead of the game. And if you caught me on this, good job. So proof, we do induction on it. Now, let u and v be n r to the n. Okay? Now, that I'm not gonna write. I was gonna write it out. You should know what that means. In fact, I just wrote it out up on the board a minute ago. Right? That means that both u and v are u1, u2, all the way up to un. V is v1, v2, all the way up to vn, and all of those values are real values. Okay. Now, in the base step, we're gonna suppose that n is equal to 1. Okay? So what does that mean for u? Well, then u is just equal to u1, and that's it. That's all that there is. And v is just equal to v1, and that's all there is, v1. Okay? And so now let's just see if this is true. Can we show that this is true? Well, u dot v is equal to, well, that's easy. It's just u1, v1, u1, v1. Okay? And so then that squared is just equal to that squared. Okay, all right. And let's compute u dot u. U dot u is just u1 times u1, which is just u1 squared. Ditto with v. V dot v is equal to v1 v1. Yeah, that's what that is, just by definition, right? So then we have v1 squared. And so, since this is equal to that times that, right? u1 v1 squared is the same thing as u1 squared v1 squared. Okay, then this u dot v quantity squared, let's write it all out here, right? Which is equal to u1 squared v1 squared, which is indeed equal to u dot u times v v dot v. So the base step holds. Base step holds, base step is true, right? Okay? So we're good to go ahead and start our induction step, right? Yeah, technically, we could just jump right into the induction step. And if you do, don't let him eat it. Just tell him not to. Try to take it away from him and maybe give him something else. So we absolutely could. Technically, we are good to just move straight into the induction step. And if you did that, you good luck. You're going to hit something and go, I have no idea where to go from here. And this, I've said this before, with induction proofs, sometimes it's really useful to go ahead and do the next step. So when n equals 1, we did this and it was super easy. Now let's try n equals 2. And again, this isn't like right now, I'm going to consider this. So like this is part of my proof. We could go ahead and put that in my write-up. But right now, I'm going to go ahead and put that over to the side. Get a new piece of paper where I'm going to do a ton of scratch work. And everything that, and like I want you to kind of keep this in mind. This is like how imagine that we're doing this together. I just wrote this on one sheet of paper. Now I'm going to put that sheet of paper aside. We're going to do a ton of work, and then we're going to come back and I'll show you what I would write at this, continuing on this part of the paper later on. Because we got a lot of work to do before we could get to that point. And so the first bit of scratch that I want to do is this. So this is not part of our proof, but this is just our work so that we have an idea of where to go. Now, what I'm about to do is suppose that n equals 2, okay? And I'm going to get rid of this because, again, this is not part of our proof. We're going to come back to that. And so imagine that line that I drew under my thing. I've just condensed it all into here, and we're going to come back there. I do want this up there so that I don't forget what I'm trying to do. And so you imagine you've taken your sheet of paper and you've put it over to either your left or your right, depending on if you're left or right-handed, and you could refer back to what you've done before. But this is the scratch work now. We're going to say, okay, what happens when n is equal to 2? If n is equal to 2, then my u is, well, I guess u1, u2. For some values, u1 and u2. They can't both be 0. Well, one of them might be 0. And this is v1, v2. Now we just want to test, does this work? I don't know. Let's figure it out. So u dot v, well, that's just u1, v1 plus u2, v2. Yeah? Okay. We're going to take that thing and square it. That's the squared part. Okay. We'll do some more work in a minute. This is just scratch work. I'm just kind of playing. I have an idea of what the left-hand side is going to look like, so let's play with the right-hand side. U dot u, well, that's just u1, u1 plus u2, u2. Oh, right, that's right. We had that written down earlier. u1 squared, u2 squared. Ditto with v dot v. V dot v is just going to be v1 squared plus v2 squared. Well, now let's see. Is that indeed less than this? Can we show that that's the case? Oh, let's see. u1 v1, u2 v2 squared. Is that less than or equal to this times this? So that's going to be u1 squared plus u2 squared times v1 squared plus v2 squared, like that. Is that true? I don't know either. I can't tell. I can't look at that and tell you if that's true. So we're going to have to actually do some work. We're going to have to multiply this stuff out. On the right-hand side, we can first outer inner last these guys and say, okay, that times that, that's u1 squared, v1 squared. Outer is u1 squared, v2 squared. Yes, buddy?
And then he's gonna climb up there.
Okay, give me just a second. U2 squared V2 squared. So that's the right-hand side. I just did first, outer, inner, last. Let me go save my child from sudden death. Okay, now the left-hand side. Okay, that's something squared, so we have to first, outer, inner, last, all that stuff. Okay, so when we do the first, we get U1V1 times U1V1. We could write it like this, U1V1 times U1V1. Okay. But I noticed that this shows up over here too. Like I could rewrite this as U1, U1, V1, V1, or in other words, U1 squared, V1 squared, right? So first, outer, inner, last, the first gives me U1 squared, V1 squared. So I'm going to go ahead and do that right here. U1 squared, V1 squared. Why did I choose to write it like that? Well, because I could see what's over here. I could see what type of thing that is, and it'd be really, since they're the same thing, they do indeed cancel. Something we didn't talk about, Justin, you just said that you can't subtract from an inequality. Well, if these two things are exactly equal to each other, we're not saying this is less than or equal to that. No. It's always the case that no matter what's over here, I don't know, z, and y also plus x, you could always subtract the same thing from both sides. So I'm looking for that. I'm hoping that I can reduce this so that I don't have a bunch of these ugly terms around. And that when I do that, the thing I get is easy. Well, that's going to, if I'm looking for stuff to cancel on both sides. Okay? That's what I want to happen. So that's why I wrote it like that. Okay? Now I'm going to do the outer and the inner. And since I'm squaring something, it should give me the same thing, right? When I do the outer, I get U1, V1 times U2, V2. When I do the inner, I get the exact same thing. And so I end up with two of these terms. And since there's a plus right there, it's plus two of these. So plus 2 times U1, V1, U2, V2. And now the last. I get that, square that term, and I get plus U2 squared, V2 squared. Nice. You see how much more involved this thing is than the base step? We'll come back to that. Okay, now let's make this simple. This thing is the same as this thing, so they cancel. This thing is the same as this thing, so they cancel. Now all I'm left with is this right here. 2U1, V1, U2, V2. And I want to know. And the whole time I'm asking myself, is this less than or equal to that? U1 squared, V2 squared plus U2 squared, V1 squared. Is that true? I don't know either, right? What can we do? Well, oftentimes, and this is a good trick to have in your toolbox here, is if you're trying to show that something's less than something else, or something's greater than something else, sometimes it's easier to show that something is positive. In other words, what I'm saying is, let's take what's on this side of the equation and move it to this side of the equation. Because if I bring him over here, I'll have 0 less than or equal to, and we want to know, is that true? And watch how I'm going to write this. Minus 2 U1, V1, U2, V2 plus U2 squared, V1 squared. Okay. Sometimes it's easier to show that a certain quantity is positive, say, or negative. We could have taken it over to the other side, whatever, but sometimes it's easier to show that something is positive rather than something like this, right? And you could try, you could say, well, what if we divide everybody through by U1? That's going to give me a U1 in the denominator. What if I divide by V1? And I could kind of see, yeah, if I'm trying to, I don't really know what to do here. A good trick of the trade is, well, maybe if you just try to show that this quantity is positive, your life will be easier. Now, remember earlier, just a minute ago, we took something and we squared it, and we ended up with some stuff squared plus 2 times something plus some other stuff squared. This looks very similar, doesn't it? We have something squared. We have 2 times something. and we have something squared. In fact, I could rewrite these here as u1 v2 quantity squared. I could write this right here as u2 v1 quantity squared. And that's the case. Maybe since I've grouped the u1 and the v2, that's what I'll do right here. I'll group the u1 and the v2 together. u1, v2. And since the u2 and the v1 are together here, I could group that. I say u2, v1. So I'm rewriting the order a little bit. But let's just check that this is the exact same thing as this. I haven't changed anything. I've rewritten it, but it's exactly the same thing. Yeah? Yeah? Now if I regroup this a little bit and say, well, this is kind of like this right here, you might notice this looks very, very, very much like you have some number, x squared, minus 2 times, well, that's the same thing as x. That's some number squared. Let's call it y. And that's y right there. That thing right there, that's a perfect square, isn't it? In fact, that's just x minus y quantity squared. Check it. First, outer, inner, last. First gives you x squared. Outer gives you minus xy. Inner gives you minus xy. For a minus, 2xy. The last is a negative y squared, gives you a positive y squared. Well, that's the exact same thing that we have right here. And instead of x, we have u1, v2. Instead of y, we have u2, v1. And so, let's go ahead and write it like that. This is what we're asking ourselves the whole time. Is this true? Is this true? Is this true? And so, I'm going to rewrite this as u1, v2 minus, since that sign right here is a minus, we're going to go minus u2, v1 quantity squared. And I'm going to check it and make sure. Does this give me that? If I take that and square it, first gives me that. Outer, inner are the same thing as u1, v2 times u2, v1. It's a minus. You have minus, minus gives you 2 of them. Yep. Okay. Then you take that and square it, you get that. Yep. So this is true. Because any quantity you have in here, I don't care what it is, when you take it and you square it, it will be bigger than or equal to 0. Okay? And so, let's think this through. Does this all work in reverse? We have, so, this is like I was saying earlier, now that we've done all this, we have to make sure that these steps work in reverse because we don't want to start with the thing we're trying to prove. This is what we want to prove, and then work our way down until we get to something true. We have to make sure that these steps work in reverse. And so, let's start. Is this true? Yes. These are all real numbers. Those are all real numbers, no imaginary numbers here. And so, it's all real numbers. You take it and you square it. It must be bigger than or equal to 0. Yeah? This, multiply it out, you get that. Yep. Rearrange those, you get that. Yeah. Yeah. Take him over to the other side and you get that. We still good? Yeah, we haven't broken any rules. That's still just that. Now, can I add this to both sides? Yeah, you could add the same number to an inequality and it is still true. Can I add this to both sides? Yeah, I could do that. So we could go from this step to this step. It's perfectly good. Now, finally, is this the same thing as that? Yeah, I think that goes both ways, right? We just take this and factor it down like that. We take this guy and factor him down like that. And so, yes, since this is true, then that's true, and that's true, and that's true, so that's true, therefore that's true. Check. Now again, we did not need to take this step in order to add it to our proof. We don't need to write this up. This is just my scratch work. But doing this right here will give us a huge hint on how to proceed when we go to do the actual inductive step, which is what we're going to work on right now. Now let's work on the inductive step. So, one thing that we absolutely have to have is an inductive hypothesis. Otherwise, we're not doing induction. And we have to use it somewhere in the inductive step. Maybe we want to do it at the beginning. I know you guys ended up doing that a lot with your proofs. Maybe you want to try to start with the thing that you're trying to prove, but if you do that, that's the way I want to take this one. I want to start with the thing that I'm trying to prove. And then as we move down, at some point we're going to have to invoke the inductive hypothesis. We're going to have to go from one line and say, by the inductive hypothesis, such and such. Otherwise you're not doing induction. That has to show up somewhere, okay? So let's get that down, right? So right now, right, I'm not doing a formal write-up. This is just my scratch work, and it's going to look something like this. I'm going to say, okay, this is going to be the part where I'm working on my inductive step. And so it's going to be nice to have that stuff up there. So the inductive step starts with the inductive hypothesis. So we're going to suppose that this is true, right? That's the idea, that this is true for any arbitrary n, right? Because we did the case where n was equal to 1. We actually did the case where n was equal to 2, didn't need to, but now we're going to suppose that it works for when n is 3, when n is 4, when n gets all the way up to n, okay? So suppose that this is true when n equals n. But one thing that's really going to help us is if we translate this into summation notation. Okay, so we already did this earlier, right? I said that u dot v in summation notation looks like this. Suppose k goes from 1 up to n of the uiv's. Or, I'm sorry, k. ukvk's. Okay, suppose that. So I'm just translating this statement right here into summation notation. Suppose. Now, u dot u is the sum. K goes from 1 up to n of the uk's squared. Not that whole quantity squared, just the uk's are squared in there, right? So in other words, u1 squared plus u2 squared plus all the way up to un squared, that's what u dot u is, right? And so I just translated this into that and then said that's the same thing as that. Same thing here. Sum as k, 1 up to n of the vk's squared. Okay, so that's the inductive hypothesis right here. And I'm going to abbreviate it, IH. And so that must show up in my proof. I have to, at some point, say, because this is true, then the next step is true, or something like that, right? By the inductive hypothesis, such and such. Okay, so I want that somewhere on my page as I'm doing my scratch work so that I don't forget that that has to show up somewhere, okay? All right, so that's somewhere. That's in the back of my mind. Actually, that's in the very front of my mind. Now, we must show what? Well, we have to show that it's true for n plus 1. What would this look like when n is no longer equal to n, but when it's equal to n plus 1? Now, I might have made this a lot easier if we started with m here, and that these are n r to the m. And now we're doing n. At any rate, I hope this isn't too confusing because I made a big stink about using k. I'm sorry, but this should make sense, right? So we're supposing, so now that we've proved that it's the case when you had a 1 vector, we're supposing it's true when you have a 2 vector, and when you have a 3 vector, and when you have a 4 vector, and when you get all the way up to the n vector. Now, if we could use this to show that it's true in the next step, in other words, an n plus 1, then we'll have an induction proof. And we could show that this is always true, no matter how big or small n is. Okay, well, I guess n can't get below 1, but anyway. Okay, so we must show, well, it's the same thing. The only difference is instead of going up to n, your sum is going to run up to n plus 1, right? So you have the sum as k goes from 1 up, instead of now to n, you're going up to n plus 1. UK VKs squared less than or equal to the sum as k goes from 1 up to n plus 1 of the UKs squared. Now the sum as k goes from 1 up to n plus 1. The next step, VK squared right there. That's what we must show right here. So now here's the big question. I have to show this is true. Have to use the inductive hypothesis. And generally, we want to start with one or the other. Okay? And the question is, which one of these do we want to start with? And so I can think, well, maybe I want to start with the inductive hypothesis just to get it out of the way. Then I don't have to worry about using it. I could just start with it. So let's imagine that we do that, right? I'm going to say, okay, by the inductive hypothesis, and I write this down. Now I need to get from here to here. It's like, well, I could add the same thing to both sides of an inequality, but if I add to here, well, now I have this squared thing. I mean, I can't imagine what I could add to this thing squared, some term here. Now I have to somehow bring it into the squared. Yikes. And then what could I, and if I do that on that side, and now I have this product, if I add that over here, how do I get that into the product? I don't know. I'm not quite sure how I could go about doing that. It looks very complicated. Maybe there is a way. Maybe you could figure it out. That would be interesting. If you figure that out, email that to me. That would be interesting. But I cannot see an easy, straightforward way of going about doing that. Looks like you'd have to multiply both sides by something to get that to go into there. But then you've multiplied a sum by something. And one thing we're going to really want to keep in mind here as we go to do this is that when you have the sum of something, okay, this thing is a sum, right? It's a1, a2, all the way up to an. And so when something gets multiplied by it, like, I'm not going to use parentheses for these things. And if I multiply some constant by it, if I multiply this side by, say, c, I'm going to write that right out here. I'm not going to bother to write the parentheses. But you have to, as you see these things, think about, like, there's ghost parentheses there, okay? Like, this is one thing, right? And when you multiply something by that one thing, these parentheses are there. We're just not writing them every single time. And yes, I have written parentheses around them. You'll see. You'll see what I'm getting at here in a second. Okay? So, I do not see a straightforward way of starting with this and ending there. So my next thing is, well, maybe if I start with the thing I'm trying to prove, operate on that, then maybe I could come up with something true. But now I've got to be careful. Because remember the example I did with sine and cosine, right? We're starting with something we want to be true. And we're going to take a bunch of steps, hopefully ending up with something that is true. Then we're going to have to make sure that everything works in reverse. So right now, now that I've made this decision that I'm going to start here, I must show that this is true. So this is my scratch work. This is not how I'm going to write it out, because I'm starting with the thing I'm trying to prove, okay? So I'm just going to write it out. But what I'm thinking about, what's going through my head as I do this, is, okay, every step I take, I'm going to have to make sure that going from this to that does work. Just like with the sine and cosine thing, right? So, okay, that's in the back of my head as I'm doing this. All right, so the sum. This is the thing I want to show to be true. 1 up to n plus 1 of the UK's squared times sum, k equals 1, n plus 1 of the VK's all squared. Here's a trick. I'm gonna tell you a trick. So, and this is a very useful trick whenever you're working with sums. Is that sometimes it's nice to peel off a term. Okay, so this is what I mean in particular, right? So if you have sum 1 n, let's say, of course, what is this thing? Well, it's just this right here. It's a1 plus a2 plus a3 all the way up to, how about an minus 2 plus an minus 1 plus an. All of that bad boy right there, is this guy. But we could rewrite that, if we were so inclined. We could pull off a term and say, well, that's the same thing as k equals 1 up to, how about n minus 1 of the AKs, and then we just plus that last term. You could also do this from the other direction, right? You could say, well, there's that whole sum that we're working with, and we could have pulled that term off. In other words, we could group it right here and say, okay, that's the same thing as a1 plus this sum, now as k runs from 2 up to n of the AKs. And you can pull off more terms if you want, if you need to, right? It's just, whenever you're working with sums, this is something you want to have in the back of your head. Like, maybe this will help, maybe not, I don't know. But the thing is, why would I even think about this? Well, we're starting here with this thing. I know that I need to use this thing somewhere. And I could make this thing look a lot more like this thing if I pull off that last term. Right, so like for instance, if this, instead of going up to n, went up to n plus 1, well then we have all these terms right here, n plus 1. And I could regroup this sum. So what I just wrote, just to be clear, this thing is this whole thing right here. And I could peel off the last term by just running this from 1 up to n of the AKs, and then having my an plus 1 here at the end. The benefit to that is, like I said, this, right? If I pull off the last term here, then the thing that I'll be left with is indeed this type of thing right there. So I have no idea how this is going to come together. I'm just doing scratch work, but I'm thinking, if I need to turn this statement into this statement, maybe I could start by rewriting these statements so that they look a little bit more like that, so that these terms actually show up in the thing that I'm working with. So that's all I'm going to do right now. That's my first step. I'm going to say, okay, so let's start with the thing that we're trying to prove, and let's just rewrite it. Okay, so I'm going to rewrite this as the sum as k goes from 1 up to n of the UK VKs plus what? What should that last one be? We pulled off the n plus 1 term, so this would be un plus 1 v n plus 1 right there. This is less than or equal to. I'm going to do that right here. I'm going to pull off that last term and make this sum run from 1 up to n, and these are the UKs squared, plus the last term that I've pulled off, which is just u n plus 1. Same thing right here. Okay, so that's the sum as k goes from 1 up to n of the VKs squared, plus that last term that I pulled off. Ooh, look what I didn't do. It needs to be squared. These are squareds, right? Right? Yes, everybody with me on that. So this is going to be n plus 1 quantity, or that little guy squared right there. Okay, I can see I'm a little bit closer. This looks more like this type of thing. Okay. Now, this is where that extra work we did is going to start to pay off. Because earlier, we did the base case where n was equal to 1, and it was too simple. It was like, that is equal to that, and so it's true that it's less than or equal to that, so yeah, we're done, right? But then when we did the case where n was equal to 2, we actually had to square some stuff out. Well, it looks like we might need to square some stuff out. And now that we've done that second step, I feel more confident about doing this. It's like, oh yeah, this is the kind of thing that we just ran into when n was equal to 2. And so, if I didn't do that step, I might be sitting here looking at this and going, oh no, am I really going to have to multiply this out? Is that going to get me anywhere? Am I going to waste like an hour trying to do all this? But now that I've done the step where n was equal to 2, and I did all of that multiplying out, and then it did work, I feel more confident now that if I continue on by just multiplying these guys out, then maybe I'll come up with something that does actually work, and I'm not just wasting my time. So let's do it. Let's multiply this stuff out. So one more time, just so we know what we're doing here, we're trying to show this. So that's what I'm going to start with. I took a step. Why did I take this step? Well, because the thing that I need to use somewhere along the way had things that look like this. I was able to rewrite these things so that they look more like these things, right? And so hopefully, if everything works out, then yeah, that's the idea. And now finally, since I'm starting with what I want to prove, and I'm moving in this direction, hopefully towards something that I could show to be true, I need to keep in mind, does the reverse step work? So if we can somehow start with something true and work our way up to here, can I go from here to here? And the answer is yes, because I haven't changed anything. I've just rewritten the way this looks. If I wanted to, I could do this entire thing without summation notation. I could go u1 v1 plus u2 v2 all the way up to un vn plus un plus 1 vn plus 1. Take that and square it. Make that less than u1 squared plus u2 squared all the way up to un squared plus un plus 1 squared. And I'm going to stop right here because you could see this starting here. It's going to be much, much worse. But really, this is what this is. There's no difference here with these things. It's just that I've chosen to take this part of that and rewrite it in a nice, clean, easy form. I'm taking this part of that and writing it in this nice, clean, easy-to-use form. You could do this, though. This would work very well. Oh, it would work. I don't know about very well. It would work, it would just be very hard to keep in mind what's going on. Okay, so now let's actually do this. Let's square this side out. First, outer, inner, last, okay? When I do my first, I'm remembering here that that's just a sum, right, of stuff. And so it's whatever's in parentheses, it's a bunch of stuff in parentheses, and when I square it, well, I just get whatever's in those parentheses squared, right? I don't get it's not the individual ones that are being squared. I'm not squaring each one of these guys because that doesn't work. Remember, I warned you about that. It's that this entire thing gets squared. So let's rewrite that with added parentheses just to help us out. It's that this thing gets squared. What is that thing? Well, it's the sum. This k goes from 1 up to n of the u, k's, v, k's, right there. Now, outer, inner are going to be the same. It's going to be this thing times that. And like I said, when I have some constant and I'm multiplying it by a sum, I'm just going to go ahead and write it on the left-hand side. I'm going to say that's the same thing as un plus 1 vn plus 1 times the sum, uk's, vk's, k goes from 1 to n. And remember, right, that is shorthand for all of this. u1, v1, all the way up to the un, vn's. And then on the very outside, we have the un plus 1, vn plus 1. That's what that is. I'm just not writing the parentheses around this because I just have a ton of parentheses, right? So that's standard to do that, okay? So that's what we get from the outer multiplication. When we do the inner multiplication, we get the same thing, and so we end up with two of these bad boys right there. Does this look familiar? Does this feel familiar? It does, because we did the second step, which wasn't necessary, but it will help us. So I feel good about this. I feel like, all right, I'm heading in the right direction. Now, finally, first, outer, inner, last is going to be that times itself. So there's a couple ways we could write this. I mean, I could write it as un plus 1, vn plus 1 all squared, or I could write it as un plus 1 squared, vn plus 1 squared. Either way, it's about the same. I just chose to do it that way. Okay. Now, the right-hand side. We're going to have to first, outer, inner, last. Oh, and by the way, the whole time I'm asking myself, is this true? Is this one true? Is this one true? Right? That's what I'm doing here. Okay, first, outer, inner, last. That's this big sum times that big sum. So I'm just going to write them as that times that. Okay, so I have the sum k equals 1 up to n of the uk's squared times sum k equals 1 up to n of the vk's squared. So that's my first, that times that. Outer gives me that times that. So I'm going to write that as vn plus 1 squared times the sum, as k goes from 1 up to n of the uk's squared. Inner gives me that times that. U n plus 1 squared times the sum, k goes from 1 to n of the vk's squared. Finally, that times that is my last. So u n plus 1 squared, v n plus 1 squared. Okay. Now, I see something that's easy to cancel right away. It's that this is the exact same thing as this right here. So I'm going to go ahead and cancel it. Actually, one thing I didn't do is stop to check. Does this work in reverse? Well, yeah, all I did was just multiply it out as sum. Right? There's nothing, inequality or not, this is the exact same thing as this, right? This is just like if you had a plus b, c plus d. This is the exact same thing as ac plus bc plus AD plus BD, right? It's just each one of those are like that, right? So this is the exact same thing as this. There's no problem going from this step back to here. Ditto over here. This is just a perfect square, right? We take a binomial, square it. This is the thing you get. So it works in reverse. So we are good up until now. Now, I'm going to cancel things on both sides. That's perfectly fine. I could cancel that. That. And now, lo and behold, there's the inductive hypothesis. Look at this. There's that guy on that side. There's that guy on that side. Ooh. But we can't subtract inequalities. Remember that problem I said at the beginning, right? Like we went into this before we even started the proof. It was like, I have an inequality. Here's my inequality. And I know that that's less than that. I can't just subtract it off. But we don't care about this direction, do we? It's a little weird. We don't care about going in this direction. What we need to ask is like, yeah, we want to end up here. We're not starting with this and trying to derive something. Hopefully all of this work that we're doing, we're going to end up with something that's true. And then we're going to ask, can we go from this step to that step? Can we go from this step to that step? Can we go from this step to that step? And so I'm imagining, let's say, here's this guy right here, and this guy right here. Going from here to here, canceling those, technically does not work. So give me just a second to write this out. K equals 1 up to n of the uk's vk's less than or equal to, he's gone, and now we're just left with these two guys. Vn plus 1 squared, the sum is k equals from 1 up to n of the uk's squared plus u n plus 1 squared, the sum, k goes from 1 up to n, of the v, that's a good u, vk's squared. Now remember, okay, so I just said, you can't do this. You can't go from here to here and hope that that's okay. But we can go from here to here. Why? Because this is the thing. You can add inequalities. If this is true, so this is the hope, that we're going to do some work and show that this is true. So then we're going to start with something true. work our way back until we get to here. And then from here we could say, by the inductive hypothesis, I can add this to that side and this to this side to get back to here. Does that make sense? In other words, we have some stuff and we've ended up at this point here. A is less than B, right? And we've been moving in this direction, hopefully from truth. Hopefully we'll end up with something true, and then we're going to ask, can we work our way back, work our way back, work our way back until we get to here, which is just something being less than or equal to some other thing. And then we're going to say, and inductive hypothesis gives us that C is less than or equal to D, the C in this case being that guy, the D in this case being that guy, and saying, well, moving backwards, it must be the case that A plus C is less than or equal to B plus D, which will give us that right there. And so we are good. Even though the step that we're taking right now isn't exactly, you can't do it if you're trying to go this way, the step in reverse will work. So, we're good to go. We're going to keep going. But now here's the hard part. We have to show that this is true. Is that true? Does that look true to you? Well, maybe looking at this it looks familiar. Maybe it looks similar to something that we did recently. Maybe it looks like this, the case when n equals 2. And we have 2 times some stuff multiplied by each other. And on this side we had some squared stuff plus some other squared stuff. And I guarantee you, if we did not do the case where n equals 2, you would get to this point and go, I have no idea what to do. I really have no idea what to do right now, because look at that. How could I show? Maybe I could divide by something. Maybe I could add something. Does not look easy to do at all. But now that we've done that step, we kind of remember we had like a 2 with like a u and like a v and like a u and a v or something. And that was less than like some u's and some v's squared, and some u's and some other stuff squared. And then we brought that guy over and he turned out to be a perfect square, which was indeed bigger than 0. So maybe something like that's going to work over here. So that extra step we took has now informed me on which direction to go now. Whereas I would have had no idea if I didn't take that second step. So the second step was not necessary for our proof. And when we do our write-up, we're not going to write it down. But doing the actual work has now got me to this point. I'm going to go, well, you know what? Maybe if I bring him over the same way that I did before. Which I need some room now, so I'm going to go ahead and write over here. Here's my 0, less than or equal to. So bringing him over, and again, I'm going to put him in between, the same way I did earlier. So that's going to give me this right here. Here's my v n plus 1 squared times this big old sum of k equals 1 up to n of the uk's squared, minus this stuff, minus 2 times un plus 1 v n plus 1 times this big old sum, which k goes from 1 up to n of the uk vk's, plus this guy, plus u n plus 1 squared times the sum k equals 1 up to n of the vk's squared. And that's my big question is this guy positive? Okay, we're still asking this question the whole time. We're saying, is that true? Is that true? Is this true? Now you might be tempted to jump the gun and say, oh, we'll do what we did last time. Because look, I could just say, this is like having my vn plus 1 and my sum of the uk's, and then I'll go and square them. But I warned you about this. I already warned you about this. Don't do that. That's not true. You can't have a sum of squares, u1 squared, u2 squared, all the way up to un squared, and then say that's the same thing as just the u's squared. That's not equal. You can't do that. So I'm looking at that and I'm thinking, Well, it'd be nice if I could write that as one thing squared. And then maybe something will work there. And it'd be nice if I could write that as one thing squared, but I know that that does not work. So what do we do? Yeah, I'm thinking it's going to be like the thing we did earlier, hopefully. I mean, like, look at that. You have a squared thing, minus 2 of something multiplied by something else, plus a squared thing, but we have these sums of squares, and it's not really working. So what do we do? Well, there's another rule of thumb, or another trick. When it comes to sums, when it comes to summation notation, when in doubt, write it out. I was going to try to cram everything down here, but we could. It's going to get really ugly. So what I'm going to do, I'm going to erase a bunch of stuff here. But before I do that, I want to make sure that all of these steps are reversible. Because I'm remembering, hopefully I end up at something true, and then I want to be able to work my way back. And so let's just make sure that all of these steps work, okay? So if this is true, and we're hoping we get to something true, we work our way up, and then get this. So we're going to suppose if that's true, is that true? Yeah, all we did is we took an inequality and then we brought somebody over. So that's perfectly fine. Now, from this step, we could add this to both sides. No problem there. Yep. By the inductive hypothesis, we'll be able to add this to the left side, that to the right side. Right? So we'll be able to go from here to here. This is the same thing as that, so we could go there. This is the same thing as that, so we can go there. So from here to here, we're good. Finally, this, can we go from here to here? Yeah, we just rewrote these things. And so that is exactly the same thing as that. That's exactly the same thing as that. That's exactly the same thing as that. So hopefully if we get back to here, then I'm sure we could get to where we want to go. Okay, so now I'm just going to erase, I'm going to copy this part back down up. So from here, again, when in doubt, write it out. So I'm just going to expand each one of these sums, and hopefully something's going to work out. I'll see something. We're asking, is this stuff positive? Is this stuff bigger than or equal to 0? So we have Vn plus 1 squared times this nice long sum, which is u1 squared plus u2 squared all the way up to un squared minus 2un plus 1 vn plus 1 times u1 v1, u2 v2, all the way up to un vn. The last one is un plus 1 squared times the v1 squared plus the v2 squared plus all the way up to vn squared. Okay, is this true? And it's still hard to see, so I don't know, maybe if I distribute these guys in, maybe I'll see something. I mean, this is looking very good. I mean, I have squareds, I have minus mixed terms, and then plus squareds. Maybe, I'm hoping I could rearrange this or something. So, is this positive, we're asking. And so, okay, I have a few choices on how to do this. But I'm kind of thinking back to the case when n was equal to 2. We had like a bunch of mixed terms and stuff like that, and we ended up having to rewrite them. So for right now, what I think I'm going to do is just kind of continue with this convention where I have my u's in front of my v's. So when I bring him in to distribute him into here, I'm going to do the u's first. So that's going to give me a u1 squared vn plus 1 squared plus the u2 squared vn plus 2 squared all the way up to the un squared v n plus 1 squared. Now, here's the hard part, right? I want to be bringing him in, the minus 2n, un plus 1, vn plus 1. And that's going to be the u1, v1. I'm going to bring him in here, and we're going to get a minus 2 un plus 1, vn plus 1, u2 v2, and so on. I'm already noticing like the way that these are going to be grouped, right? We're going to have the UK's always with the, look at that, I did it n plus 2. That's not okay, that's not good. It's an n plus 1. But the v n plus 1 always comes after one of the UK's, right? And so I'm going to choose to rewrite it kind of that way, right? With these guys on the left, I'm going to have my u1 grouped with the vn plus 1. So I'm going to rewrite that as 2 u1 vn plus 1. And then I'm anticipating what's going to happen here. I'm going to be writing all of these as my un plus 1 squared, and then one of those vk squareds. And so I'm going to take my vk, which is 1 in this case, and group him with the n plus 1. So un plus 1 v1. I wouldn't think to do this if I hadn't done the case when n was equal to 2. Because I remember we had to rearrange some stuff to make it more obvious. So I'm going to go ahead and do that rearranging right now, anticipating that hopefully all this stuff is going to work out the same way. And so I bring him in and I get a minus 2. How did I say I was going to write this? The u1 vn plus 1. u1 vn plus 1, un plus 1 v1. Then it comes into the next one with the 2's, and I go minus 2. Again, now it's going to be u2 vn plus 1, right? The u2 and the vn plus 1. And then the un plus 1 and the v2. All the way up to minus 2 un vn plus 1, and then vn plus 1 vn. vn plus 1 vn. I'm already running out of room on that line. Okay, so we got all of those. I've distributed him into each one of these in the sum, and then I just went ahead and rearranged the order. Right? Now let's get this last bit out here. And so that's going to give me, I'm just going to start him right here. So here's the plus un plus 1 squared v1 squared plus un plus 1 squared v2 squared, all the way up to un plus 1 squared vn squared. Oops, I didn't write my ellipsis. Let's do that. Dot, dot, dot. All the way up to un plus 1 squared vn squared. And now, see, it's a little bit, it's a lot bit more complicated than the first case, when everything just happened to be a perfect square, but I could see that these things, if I regroup them, they will be perfect squares, because we have our u1 vn plus 1. Here's my u1 vn plus 1. un plus 1 v1, plus 1 v1. So if I group the first term from here with the first term from here with the first term from here, it looks like I'm going to get a perfect square out of that. So I'm going to rewrite that here. I'm going to say there's this one, and this one. I'm going to group together. So we have my u1 squared vn plus 1 squared minus 2 u1 vn plus 1 un plus 1 v1. Finally, that one is plus un plus 1 squared v1 squared. Now let's do the second one. So that's going to be u2 squared vn plus 1 squared. So that's the first from there. I'm sorry, the second from this part. Now let's take the second from this part, which is this, minus 2u2 vn plus 1 un plus 1 v2. And then the second one from this one, which is plus un plus 1 squared v2 squared. Okay? So now we do all of those, we do every single one of those the exact same way until we get down to the last one of each of these terms. And we get un squared v n plus 1 squared minus the last of these, which is 2 un v n plus 1. Oh. I messed that up. That should have been, oh no, un v n plus 1. That should be a u n plus 1, sorry about that. That's a u, yeah, because each one of those was a u. Okay. U n plus 1, so you see I messed that up. Sorry about that. And then vn. And now the last of those terms, plus un plus 1 squared vn squared. Now finally, each one of these groups of three, these three terms, and so on and so on and so on down to these three terms, these are all perfect squares, right? Let's just write it out. How did I know how to do this? Well, because I did the case when n was equal to 2, and then I anticipated maybe something like that's going to happen. And indeed, that's what we're seeing, okay? So it looks like we could rewrite this as like u1 v n plus 1 squared, and rewrite that as a minus 2 u1 v n plus 1 times un plus 1 v1, and then go plus un plus 1 un plus 1 v1 right there squared. Yes, let's just make sure that's that. Yeah, that's that. Yeah, that is that right there. Yep. And so that, by the way, is a perfect square, and it's what you would get if you had u1 vn plus 1 minus the un plus 1 v1, and you took it and you squared it. It's easy to see when you have it this way, right? But let's just double check, right? We want to keep double checking, and I didn't do that with this step. Obviously, these all factor back out into that. Obviously, this is the exact same thing as that. So yes, we can move in this direction, the direction we want to go. Okay, and same thing here. Let's make sure that when I take this and square him out, that we do get this bit right here. Okay, so first, outer, inner, last. This times itself gives you that, or that, u1 squared vn plus 1 squared. Yes. Now, that times that, the outer and the inner, they're the same thing. You get a u1 vn plus 1 times a un plus 1 v1, and you get two of them, and they're both negative, and so you get minus 2 of that value. Yes. Then the last bit is negative. When you square it, it becomes positive. Yep. And it's a n plus 1 v1 quantity squared, which is the same thing as n plus 1 squared v1 squared. Hello, yes, it works. Okay, excellent. Similarly, this guy turns into plus u2 vn plus 1 minus un plus 1 v2 squared. Let's check it. First, outer, inner, last. First, square it, gives you that. Yes. Outer, inner gives you u2 vn plus 1 and un plus 1 v2. Yes. And there's two of them, and they're negative. Yes. Minus 2 times that value. Yes. The last is a negative. You square it, and you get that. Yes. Okay. And you keep going. The pattern continues. It's exactly the same pattern all the way up to the very end here, where we get un vn plus 1 minus un plus 1 vn quantity squared. Is that the same thing as that little bit? That squared is that. Outer, inner is that. You get minus 2 of them. Yes. That squared is that. We are good to go. Now, the only question that remains is this positive? I've asked you like every step. I'm like, is this true? Obviously now. we can see that this is true. Why? Because these are all real numbers. Every single one of these u's and v's that we have in here are real numbers. If you take two real numbers and multiply them together, you get another real number. Ditto over here. Subtract one from another, you get another real number. It might be negative, it might be positive, but who cares? Because you're going to take that number and square it. You're going to take that number and square it. You take that number and square it. And so you have a bunch of positive numbers. They might all be zero. I guess it's possible that they could all be zero, in which case, still true. If they're not all zero, they're all positive. So you add a bunch of positive numbers together and you get a number that is indeed greater than or equal to 0. And so this is true. This is true. Yes, we can do that. And so now the question is, can we take every step back? Well, luckily we've been checking every step along the way. And so this does give us that. That does rearrange to that. That does factor out to this. This can be rewritten like that, and we already checked all the other ones, so we're good to go. So now I'm done with my scratch work, and we're ready to actually write up the proof. So now we've finished all of our scratch work, and we have it all written down on our page, and we're ready to go back to the original proof. Okay, so remember, I drew that line right there, right? So now we're going back to that sheet of paper where we're actually doing our proof. We finished the base step. We don't need to show the case where n equals 2 because that only helped us with our scratch work. Okay, so now right after the base step we're going to say now inductive step. And we're going to start with the inductive hypothesis, which is this. Suppose that, and actually, this is where it's kind of tricky because what are u and v? Like, and so up here in the theorem, we've already written that u and v are vectors in r to the n. Okay, so like if I were grading you and you went right into this, I wouldn't worry about like having said anything like that. Like having, restated like let u and v be vectors in this, in here, and suppose that this is true. It's already in your statement of the theorem, so I mean technically you're good. Now this I'm being a little bit sloppy, is because I'm saying we must show that this is true, but where did that n plus 1 come from? Like we never talked about vectors u and v being in r to the n plus 1, so again I probably wouldn't dock you for this, for not stating it, but if you wanted to really dot all your I's, cross all your T's, what you could do is say, let u and v be in here, and suppose that this is true. In other words, you're saying that for all vectors, all n vectors, all real vectors of length n, suppose that this is true. And what we're going to do is then, after saying that, now say, let u and v, and if you really wanted to be cool, you could give them different names, because we've just said that this is true. So maybe we want to call them A and B. Again, we're kind of getting into the weeds here, but now you could say let here be in r to the n plus 1. All right, so we're saying take any two vectors in r to the n plus 1. Now what we must show is that this is true. Now when you say what is u n plus 1, you understand that it's part of u, because now that u is in r to the n plus 1, you have u1, u2, up to un, and finally un plus 1. And so now writing, this un plus 1 here, it's actually defined now that you've said something like this. Again, I'm being really pedantic. I'm trying to give a perfect proof here. But it's understood what you're doing. I wouldn't worry too much about this, because the bread and butter is in the actual thing the actual work that we've done. Okay, so technically we're saying, okay, now suppose that u and v are any vectors in r to the n plus 1. Then what we must show is this right here. Okay, so to that end, now remember, we're going to do this in reverse. We're going to write it, we're going to start with something that's true and end up with this that we're trying to show. So I'm going to say, like we just did, suppose that this is true. That's your inductive hypothesis. We need to use it. And given any u and v in R to the n plus 1, take the ui's and vi's. You really don't need to write this, but I'm just saying, like, this is what you're going to do, right? Like, given any u and v, okay, you've given me one, okay? It's like 1 minus 1, 7, 4, pi, 9, right? Take all of those values and do this. And observe that I'm looking at the notes, right? These are my notes. This is the scratch work that I did. And observe that this is true. u1 vn plus 1 minus un plus 1 v1 squared plus, and when we did this, I did it with a second term. You know, I'm going to cut to the chase here and just do the first and the last term. Okay, so I'm going to say, okay, yeah. All the way up to u n v n plus 1 minus u n plus 1 v n squared is positive. Observe that this is true. Is that true? Yes, absolutely. You have a bunch of real numbers because u and v are real. And so all the ui's and vi's are real. They're all well defined because you've given me those two values. And so each one of those is good. You're not just pulling out a un plus 1 out of nowhere. They've been given to you. Okay, boom, there you go. Observe that that's true. Yes, it's true, isn't it? Yeah. Okay, now from here, let's square it out. So that gives you, oh boy, u1 squared vn plus 1 squared minus 2u1 vn plus 1 un plus 1 v1 plus un plus 1 squared v1 squared. Yeah. Plus all the way up to the end, which is un squared vn plus 1 squared minus 2 un vn plus 1. You notice how I'm not looking at my notes right now? That's because I'm actually trying to verify this as I do it. Like, this is easy. I've been squaring stuff out for a long time now, and so I can just look at this and write it down without looking at my notes. It's a really good habit to get into as you start to do this. If there's an easy step to take, actually do it. Actually verify it as you're doing it. Is that right? Yes. Now I'm going to look at my notes and go, is that what I wrote on my notes? Yep, that's it. That's the thing. Okay. So now what did we do on the notes? Oh yeah, we rearranged them. We put all of the 2's together. We had all of these first ones together. All of the 2's were together, and all of those were together. So let's do that. We had u1 squared vn plus 1 squared plus all the others that we didn't have, all the way down to the last one, which is un squared vn plus 1 squared. And I'm checking to make sure, yep, that one's that one. I haven't changed anything. I'm just rearranging the sum. Now, minus 2u1 vn plus 1 un plus 1 v1 minus all those other ones that I didn't write, minus the last one, which is 2 un vn plus 1 un plus 1 vn. Yep. Plus now all the last terms, which are these guys. un plus 1 squared v1 squared. Then the un plus 1 v2 squared, un plus 1 v3 squared, and blah, 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 blah. All the way down to the last one, which is un plus 1 squared vn squared. Did I do that right? I think so. I'm just going to check. I just rearranged stuff. I took all the first bits, put them over here. Took all the minus 2 bits, put them here in the middle. Took all of the last bits and put them here at the end. Now let's factor stuff out. And I could look at my notes and say, yep, then that was when we factored stuff out. And what I'm going to do to check myself is just to actually do it. So I'm going to look at this in 0 less than or equal to Now, those u's run from u1 squared, u2 squared, u3 squared, all the way up to un squared. And the vn plus 1 squared is the common term in all of them, so I could pull it out. I'm going to pull out the vn plus 1 squared, which is leaves me a u1 squared all the way up to my un squared. Pulling out common terms, I could pull out a negative 2, and it's the n plus 1s, the vn plus 1, un plus 1, the vn plus 1, un plus 1 that comes out. So I'm going to write it as un plus 1 vn plus 1, which has been factored out of each of what? Well, u1 v1. The next one was u2 v2, u3 v3, all the way up to un vn, right there. Double checking myself. That goes back in. Yeah. And, you know, I'm not including the second term in each of these like we did when we did the work. If you're really unsure, like, because I'm 100% sure that we got this right, but if you're not, it's a little bit more to write. It could be kind of a pain, but you could be extra sure that you're on the right track, because this is kind of hard to see a pattern here when you only do the first and the last bits. When you do the first, the second, and then the last, you could kind of see the pattern a little bit better, right? Because we would have a u1 v1, and then a u2 v2, and all the way up to un vn. Here we'd have a v1, a v2, all the way up to vn. And so, but it's not necessary. I'm 100% sure this works. Now, in the last bit, there's a un plus 1 squared in each one of these terms, so that's what I'm going to pull out. un plus 1 quantity squared times v1 squared, v2 squared, v3 squared, all the way up to vn squared. Okay, now what did we do? Right, then we had it in summation notation. So let's just check, is this working? This is positive. Observe that that's true. Yes, it's true. That's the same thing as this. That's the same thing as this. I just rearranged it. That's the same thing as this. I just factored out common terms. Okay. So that's going to be the same thing as this. This is just vn plus 1 squared times the sum. This k goes from 1 to n of the uk's squared. Minus 2 times un plus 1 vn plus 1 times the sum. As k goes from 1 up to n of the uk vk's. Plus un plus 1 quantity squared times the sum. This k goes from 1 up to n of the vk squareds. Now where do we go from here? I think the next thing we did is we had brought that from over here. So that's what I'm going to do. I'm going to bring him over, and I can see that, yeah, I could do that. I could add this over there. Perfectly good. Look at my notes. Yep, that's what we did. Okay, so writing him on the left-hand side, we have 2 un plus 1 vn plus 1 times the sum. This k goes from 1 up to n of the uk vk's. He is now on that side of the inequality. I brought him over. These guys remain. Vn plus 1 squared times the sum. K goes from 1 up to n of the uk squareds plus un plus 1 quantity squared. K goes from 1 up to n of the vk squareds. Okay, now here's the thing. By the inductive hypothesis, because if I went all the way without using the inductive hypothesis, none of this works. We have to use the inductive hypothesis. So this is where I'm going to use it. I'm going to say we have something less than something else. We have another inequality that tells us that this is less than that. Therefore, we could add those two inequalities, and the thing that we get is true. So, by the inductive hypothesis, just a minute, buddy. Okay, you're going to have to give me just a minute. Give me just a minute. So, that over here, that over here. So, we get the sum k equals 1 up to n of the uk vk's, that quantity squared, plus
2 un plus 1 vn plus 1 sum as k goes from 1 to n of the ukvk's. I'm going to give myself a little bit of room here because I know what's coming next. That over there, right by the inductive hypothesis, since that's less than that and that's less than that, then that plus that is less than that plus that. And so we have k equals 1 up to n of the uk squareds times k equals 1 up to n of the vk squareds plus all this junk, which gives me plus vn plus 1 squared times the sum k goes from 1 up to n of the uk squareds plus un plus 1 squared times the sum k goes from 1 up to n of the vk squareds. Okay? Boom. By the inductive hypothesis. Now, if I wasn't running out of room, I would write another line in here. But I'm not going to do that because I'm running out of room, okay? But if you really wanted to be slick, you use another line for this step right here where we say, okay, by the inductive hypothesis, this is this, okay? And now, I could add the same thing to put, and I'm looking at this. It's not like I just intuit this. I know because I'm looking at my page. Well, I could add the same thing to both sides of an inequality. And the thing that I need to add to bring all of this together is my un plus 1 squared vn plus 1 squared. So I add it to both sides. Un plus 1 squared vn plus 1 squared. I think this is it. This looks good because everything I've done works. I've used the inductive hypothesis and I used it in the right direction, right? I have one inequality, I have another inequality, and I added those two inequalities to get a new inequality that's still true. Then I had an inequality and I added the same thing to both sides. Perfectly good. But now this is the thing that factors back out to this, right? First, outer, inner, last, this guy. This is the same thing as, or unfirst, outer, inner, last, this guy. Now let's check that, make sure I did that right. First, outer, inner, last. First, yes. Outer, is that it? Yep. Inner, it's the same thing, so we get two of them. It's plus two of them. Yes. Last is that times itself, which is the same thing as that. Yes. Okay. Now, it's less than or equal to, factor this guy out, and we should get, what was it? Sum sk goes from 1 up to n of the uk squared plus un plus 1 squared. This one was the k goes from 1 up to n of the vk squared plus vn plus 1 quantity squared. Now let's just make sure. First gives me that. Yes. Outer gives me that. Yes. Inner gives me that. Yes. Yes. Last gives me that. Yes. And therefore, here we are. Look at that. The sum sk goes from 1 up to n plus 1 of the uk vk's quantity squared, because that is exactly the same thing as that. No tricks there. This is the same thing as the sum as k goes from 1 up to n plus 1 of the uk squareds times the sum as k goes from 1 up to n plus 1 of the vk squareds. as desired. This is what we wanted to show. This is exactly what we wanted to show. We must, I never even wrote it up there so I didn't lose track. We must show that that, yep, squared, yep, is less than or equal to that. Holy moly, we got it. So we've just written this. This is as desired. Alright, because this is what we wanted to show. And now let's just be really explicit here and say, and therefore, like this is the same thing as u dot v squared, which is less than or equal to, that's u dot u, that's all that is, u dot u. And this is just v dot v. I'm just saying that because that's how it was stated at the very beginning, right? Or we could say, this is true for all vectors u and v in r to the n. It would be a little nicer if at the very beginning I said r to the m, because now the n was the inductive. Yeah. But you get the idea. So this is true for all u's and v's in r to the n. And like we said, okay, so that's the end of our proof right there. That is the proof. And like I said, just to really drive the point home, right, is what was this? Well, this right here was the dot product of any two vectors. Any two vectors. There's nothing special about the vectors we chose. I said, you give me any two vectors, and this is true. You take those two, and we said that's the same thing as the magnitude or the norm of u squared, and the v, norm of v squared. And if we take the square root of both sides, since that has the possibility of having been negative, we get the absolute value of u dot v is less than or equal to the norm of u times the norm of v. Absolute value being less than something means the same thing as saying that the quantity that's inside the absolute value is bounded above by the positive and below by the negative of whatever that is. And then we could divide everybody through by that quantity, giving us a -1. There, u dot v over u v and so man. We prove this. From that, this follows that this quantity is always between -1 and 1, and therefore defining the angle between those two vectors as the arc cos of this quantity is well defined for any vectors in r to the n, no matter how big n is. So I hope this was cool. You can see why, like I said this, and I wasn't 100% sure if we were going to even get to summation notation or induction proofs, but I thought, man, we really should, because I said this in class. I don't want to just say that this, because how do you know that you can't find two vectors that like work out to be two, like when you do this? It might be the case, so maybe I'm just full of it. But I said, no, believe me, this always works. Well, now we've proved that it works. And in order to do so, we had to use a bunch of stuff that we learned this year, which I think is cool. I think it helps to bring everything back. And so this is one application of the Cauchy-Schwarz inequality. There are others. It shows up in probability, talking about, I think it's variance and covariance. Shows up in analysis a lot. Like if you ever take a course in analysis, like every other proof you do, you're going to have to say, oh, by the Cauchy-Schwarz inequality, boom. Shows up in quantum mechanics, shows up in anything with functional analysis. But yeah, and so this is very central to a lot of things. And I figured it'd be, since we had the tools to actually be able to prove it for real valued vectors, for finite real valued vectors, we might as well do it. And you can see how all this works together. So I hope you enjoyed that.